Hello to everyone. I really hope this video finds you well. My name is Artemios Oikonomou, and I'm a postdoctoral researcher at the Science and Technology in Archaeology and Culture Research Center at the Cyprus Institute. Before I start my presentation, I would like to thank the organizers of this workshop for inviting me to share some basic information about glass technology. Furthermore, you can see my email here, so please, if you have any questions, do not hesitate contacting me. So, to begin with, what is the real glass? What do we consider as glass? Glass is the youngest of the artificial materials of antiquity. As you all know, ceramics appeared first around 10,000 years ago, followed by metals around 8,000 years ago, while glass appeared quite recently, around 4,000 years from today. Real glass has a unique properties. It can be colored like no other material. It can have bright blue, green, red, yellow colors with various combinations and hues. And at the same time, it can be transparent, or also it can be completely opaque. Therefore, glass was considered as a precious material, especially in the late Bronze Age and the subsequent periods. A basic characteristic of glass is that it is an additive material, meaning that you need at least 2 or maybe even 3 raw materials to mix them in specific proportions in order to get the final product. Especially for the first millennium AD, glass, few production sites are known, while in other earlier periods the production sites are still quite unknown, and that is very intriguing for the study of glass. Let me now elaborate a bit more about the term additive material and complex material. As I said, glass is made by combining raw materials in one product. Usually, we need at least 2 raw materials, as we will see in the next few slides, a glass former and a flux. This production of glass does not leave behind many traces. There are not many production ways, which of course is bad for archaeology, and it is difficult to locate such areas. On the other hand, for example, in metal production, there are tons of waste material on site, the so-called slag, so it is easier to identify large production sites. Glass has a complex chemical composition, meaning that in one glass we can identify around 10 to 12 major and minor elements, and when we have the means to identify trace elements, then we're talking for more than 30 elements, which characterize chemical glass. This complex composition can identify the raw materials and working information, which are always important and good for archaeometry. They can offer means for comparison and correlation in order to understand technological and provenance issues. Glass is usually defined and categorized according to the raw materials used to make it. Therefore, we can have the basic categories such as plantas glass, which was mostly the prehistoric and Islamic glass, mineral natron glass, which covers mainly first millennium BC until around 800 AD, and some other special categories such as wood ash glass in medieval Europe, lead glass, and mineral glasses. In this presentation, I will focus on mineral natron glass and first millennium AD. Why we should focus on natron glass and first millennium AD? First of all, it is a long, well-documented historical period. The changes in the political framework during first millennium AD reflected also changes in glass composition. In addition, there are a lot of available analytical data of glass dating in this period, and this makes somehow our life easier. And of course, since Eastern Mediterranean and Middle East region played an important role in glassmaking in first millennium AD, this is highly relevant. During the first millennium AD, we are talking mostly about natron glass. This is the type of glass prevailing in Europe and especially in the Eastern Mediterranean and Middle East region. The glass during this period is mass-produced following the basic model of glass production, the so-called centralized model, and this is really the result of the invention of glass blowing technique, as we will see more specifically in a bit. We can consider glass as industrialized by the massive numbers of glass objects and raw glass. There are the two main production centers of glass, the Levantine coast and Egypt, where glass was produced in tank furnaces and then was further formed in glass objects in secondary glass workshops. Let's see a few technological characteristics of glass. All ancient glasses are based on silica. The majority of them belong to the so-called general category of soda-lime silica glass, or else SLS glass, meaning that three basic components form the glass. Silica is the network former, that is the basic substance that can be formed into glass, while soda and lime are called network modifiers because they can alter, let's say, the network in the desired form. Here you can see some examples of the network of silica, and here are when the modifiers are entering and modify actually this network. So soda is the flux. It can be very important for glass making because it lowers significantly the melting point of silica, and lime usually acts as a stabilizer and makes the glass more durable in corrosion factors such as, for example, water. The weight percentage of each of these basic components, as you can see, is 65 to 75% by weight for silica, 15 to 30% of soda, and 5 to 10% for lime. But where we can find in nature these components? During this period, sand is the main silica source. Sand is a multi-component material, and apart from high amounts of silicon dioxide, it also contains lime in the form of crushed shells. Glass makers usually used pure sands, or to be more precise, sands with lower amounts of impurities, and only few very specific areas in the Mediterranean had sands suitable for glass making, as it was demonstrated by an ERC project led by Professor Patrick de Vries at Leuven University a few years ago. Soda is derived from natron, which is a mineral source of soda, as we will see in the next slides. Apart from these basic raw materials, glass makers also used other additives, which were added in the form of minerals so as to offer the unique properties of glass, that is the coloration, the transparency, and the opacity. Few words about natron, in case it's the first time you come up with this term. Natron is a material widely used in antiquity, especially in Egypt, and was used as a basic component for the mummification process. It is a mineral derived as a result of the evaporation of salty lakes, and due to the high amounts of soda in its composition, was used as a fluxing agent, reducing the melting point of silica. In glass making, it was used roughly from around 800 BC up to 800 AD. Most of natron was harvested from specific locations, and especially in Egypt, at the so-called Natron Valley, as you can see here in the map in the center of this slide, or in other words, the Wadi El Natron area, which is located in the western delta of Nile River. This region, actually, a complex of evaporitic lakes, is thought to have supplied most of the natron used in the first millennium AD period in glass making. Glass production during this period follows the most accepted model so far, the so-called centralized model. Glass production can be divided into distinct steps. The primary production, which is the fusion of raw materials into glass, that means sand and natron. And in this primary production, they produce the so-called raw glass. And the subsequent forming of the objects takes place in the secondary production. These two distinct procedures were taking place also in different locations. There are only few primary workshops melting huge amounts of raw materials, as we will see later, and distributing the raw glass to the secondary glass workshops. This model takes effect, as I said, during the Roman period and thereafter, but we may suppose that something similar but in lesser extent was happening in earlier periods, such as classical and Hellenistic period. Unfortunately, there is no archaeological evidence for earlier periods of primary glass production facilities, and therefore we may assume that the primary production happened in a lower rate. So, as you can see here in this graph, which was nicely demonstrated by Freestone and colleagues in 2000. We have natron, mostly from Egypt, and sand from other sources, which are mixed together in big facilities in the factories, which this is the primary glass production, and then it was distributed in the raw glass in secondary glass workshops, where it was finally they were finally producing the final object. Primary glass making happened in the so-called tank furnaces. These are huge facilities, measuring roughly 5 meters long by 1.5 meters wide and half of a meter in height, producing mass quantities of raw glass. They date from the 1st century AD onwards and were built in very strategic places, close to raw materials and, of course, fuels. They produce around and even more than 8 tons of glass, and they needed almost 10 times the amount in fuels. That is good. The procedure to melt such huge amount of raw materials took around a month of continuous operation involving few people for the whole activity. These constructions were found mainly in the Levantine coast and in Egypt, which are the two main glassmaking centers of the first millennium AD. The amount of glass they produced was enough to create an estimation of 50 to 60,000 glass vessels. These here are the remains of a tank furnace. These big chunks of glass, as you can see here in these 3 photographs, were transferred to the secondary glass workshops, and they were formed into the final objects. The invention of glass blowing technique around 50 BC actually revolutionized the glass production as we know it today. The glass worker was able to produce a vast amount of glass objects during a day, quite easily, I would say, having an endless variety of shapes, sizes, and colors. Here you can see a nice reconstruction of a typical Roman secondary glass workshop. There are various elements, as you can see, the furnace here in the middle, where glass was fused. The glass makers who first gather the glass in the blowpipe from the glory hole, which is the opening here in the furnace. And then they make the objects. There are usually 2 openings, one from this side and another from the other side, so people can blow glass simultaneously. You can see also the stoke hole down here, where the fuels, mostly wood, was charged, and there's also the annealing oven here at the back, and here the reconstruction here on the left, where the objects were slowly cooled down. Such installations were scattered throughout the Roman Empire. Here, this is the typical composition of natron glass. Variability in some of these oxides can offer us indications of different sun sources and hence different provenance of the glass. Among these, iron is one of the elements for which we will discuss in the next few slides, since it is responsible for the greenish hue of glass that is the natural glass color. Iron oxide is derived mainly from sand, since it exists in various minerals which are part of the sand. This coloration of glass was done unintentionally, since the ancient glass makers were not able to purify sand and extract the iron content. Therefore, iron, which has 2 oxidation states, iron +2 and iron +3, in the sand is responsible for the natural color. the different hues that can be from aqua blue, blue-green, as you can see here in the left of the glass bottle, to the more yellowish colorless, let's say, color, is due to the presence of different proportions of the two oxidation states of iron. As I said, iron +2 and iron +3. This is a nice graph showing the effect of the two different states of iron. When the oxidized iron, the iron +3 prevails in the glass, then we have the more, let's say, yellowish, typically colorless glass. And the opposite happens when iron +2 is more in the glass, then we get more green, blue, and aqua blue hues. So, probably out of fashion, Roman glassmakers wanted to achieve the colorless glass. And how they could do this? There are actually various ways to do. First of all, to minimize the iron content of the sand by choosing pure suds, but of course, time to time this could be difficult and pure suds might not be available. Then they could make very thin walls of the vessels in order to have less blue-green color. For example, if you get a piece of modern colorless glass and observe it in the cross section, the glass becomes very greenish, I would say, and I'm sure all of you have noticed that. But when you see it in the smaller dimension, then it becomes colorless again. But making thin walls would make the glass very fragile. Another way could be to heat the melt for a long time, for a long period of time, in the air, that is, with the excess of oxygen. But again, this would be difficult since it would need a lot of fuel, making the whole procedure not very economically effective. And finally, to add another ingredient to chemically oxidize iron and get the colorless glass. There are two ingredients added to the glass batch with which both oxidize iron. Manganese and antimony, both are introduced in the form of specific minerals, and they can be both work as decolorizers. Here you can see the basic chemical formula describing this phenomenon. Both in class occur, as you can see here on the right table, in around 1%. Manganese sometimes is also called the glassmaker's soap, just because, in a sense, it cleans the glass from its color, and was first introduced in 2nd century BC. Antimony acts as a very good decolorant and even better than manganese. However, there are cases that researchers have noticed that glasses have intermediate values of major elements, and this led to the conclusion that glass in antiquity was heavily recycled. Here in these two graphs, we can notice this effect with the manganese and antimony decolorized glasses, and the recycled glass containing both elements, which is the result of meaning. Here, for example, we have the manganese decolorized glass. Here we have the antimony decolorized glass, and here we have some decolorized glasses containing both manganese and antimony, which is the result of recycling of pure manganese or antimony recycled or antimony decolorized glass. Something similar is shown also in the second graph, where in the upper part we have the manganese decolorized glass, and in the lower part we have the antimony decolorized glass, while in the middle we have mixed glass, therefore recycled. Now, there has been a significant amount of work by various scholars the last 20 years on late Attic glass and in general first millennium AD glass. Through this research, it was possible to identify at least 7 compositional groups with a super-regional distribution. These groups of glass were made in different workshops in the Levant and in Egypt, and can somehow easily be distinguished, as you can see here with the ellipses, using biplots. This biplot is useful for identifying primary groups of neutron glass and the ratios of certain elements associated with the sun, as for example, alumina, silica, and titanium. Here you can see the various groups having very distinct positions in this pie plot. And there's also a number of other compositional groups were used during this period, but are mostly only of local or regional significance. We can distinguish groups of glass called as Levantine 1 and 2, down here in the graph, manufacturing the Levantine coast and the large primary glass production sites such as Apollonia and Betheliger. Egypt 1 and 2, here and here, which were manufactured in Egypt. Serie 2.1 or FOA 2.1 or Serie 3.2 or FOA 3.2 manufactured also in Egypt. And of course, the other basic category of glass, the so-called HIMT glass, which was also manufactured in Egypt. HIMT stands for high iron, manganese, and titanium. So before I finish, I highly recommend watching this documentary filmed in Herat, Afghanistan in the fall of 1977. Glassmaking in Herat has been a family tradition for over 200 years and continued to be done in the same manner as described in 7th century Assyrian cuneiform tablets. So I believe it provides a lot of information regarding glassmaking. Please watch it. You can easily find it in YouTube, and you can enjoy and see all the various steps in glassmaking, both primary and secondary glass production. Thank you all for your attention, and if you have any inquiry, please do not hesitate contacting me. Enjoy. Bye.